Hi students. In this lecture, I am going to discuss problems. Let us see first one. A uniform circular wooden hoop of mass m and radius r rest flat on a horizontal frictionless surface. A bullet also of same mass and moving with a velocity v strikes the loop and gets embedded in it. The thickness of the loop is much smaller than r. The angular velocity with which the system rotates after the bullet strikes the hoop is. So your hoop means it is a ring. Rest flat. For example, this is XY plane. This board is XY plane. Then ring is now in XY plane. Okay. Let us see how to calculate. So first make the given diagram. Right, see diagram. So it is a ring of radius r mass is m. Now a particle of same mass, it collides and sticks to that, right? So we have to find angular velocity of the system after collision. See here key point is it embedded into the hoop. That means now rotation will be about the common center of mass. If you remember in earlier lectures, we have learned that, for example, this is a metric stick, or you can say uniform rod, and a particle makes a collision with the rod. If the particle sticks to the rod, then rotation will be about the common center of mass. That means center of mass of the rod and the particle system. If the particle not sticking to the rod, then rod rotates about its own axis. Now in this case, it sticks to that. That means rotation will be about common center of mass. Since both have same masses, center of mass will be at a distance r by 2. Okay, because we can replace the ring with a point mass at its center, and for particle mass is m here, separation equal to r. So center of mass will be midpoint. That means now system rotates about the common center of mass. That means we have to conserve angular momentum about same axis. Now see carefully. It is m. If velocity is v, or take it as v naught before collision, then m v naught r by 2. So we are conserving angular momentum about the common center of mass. That is equal to I omega. That is equal to I omega. Now see what is I value. I value about this axis. About its own axis per ring, mr square. But we want to calculate about this axis. So it is now plus m into distance equal to r by 2. Using parallax theorem, this is a further ring about this axis. Now for particle about same axis, distance r by 2. So plus m into square of r by 2. See how much? 1 by 4, 1 by 4, 1 by 2. 1 plus 1 by 2 is 3 by 2. 3 by 2 mr square. This is now 3 by 2 mr square into omega. Okay. So m r by 2, m r by 2 gets cancelled. Remaining is now omega equal to so v naught upon 3r. So it is just taking conservation of angular momentum. So we should be very careful about which axis we have to conserve. Since it is now sticking, we should take about common center of mass. Okay. Let us see next one. A uniform rod of length L moving down with linear velocity v naught and a zero angular velocity collides with a horizontal surface. Just after collision, the velocity of its center of mass becomes v in the upward direction as shown in the figure. The angular velocity of the rod just after the impact is, we can see diagram here, a rod having only velocity, there is no omega before collision, v naught, it is now v after collision. So we have to find omega value. Let us see how to start. So it is given initially having only translatory motion. Translatory motion, velocity v naught. It makes angle theta. After collision, velocity for center of mass, it becomes v. It becomes v. So we have to find what is omega value. Let us see how to start it. So we can see because of collision, a lot of force acts by ground on the rod for a short time interval. Because of that, there is now an impulse vertically upwards. Let us take it as J. Okay. So now we are taking, suppose this is A, point G, and this is B. So I am taking now conservation of angular momentum about point A. Okay. Then see what happens. About point A, torque is not equal to 0. So should be very careful. Gravitational force mg is acting vertically downwards, but still we are taking conservation of angular momentum. The reason is that we are taking now just before collision, just after collision. So we are knowing that net torque is equal to dl bar upon dt. So dl bar by dt. So change in angular momentum, that is equal to tau net into dt. Now we are taking just before collision and just after collision. Okay. The time gap is very small. In such a small time interval, change in angular momentum is also very small, which can be neglected or you can say which is negligible. That's why we are taking conservation of angular momentum. Now see carefully about point A just before collision. Because of this velocity, angular momentum will be, it is clockwise. Let us take clockwise as positive. Then before collision, just before collision, m into v naught into, see if you extend this line, you can see now this separation that is equal to L by 2 cos theta, right? So m v naught L by 2 cos theta, that is equal to, because of this impulse, now rod rotates clockwise. Then angular momentum about point A, it is a combination of, because of translation of center of mass and rotation about center of mass. So because of rotation, it is now I omega, and I value ml square by 12 into omega. This is a clockwise, that's why it is a positive. But because of V about point A, angular momentum will be anti-clockwise. See carefully. Because of translation, you can see R bar cross P bar. It is anti-clockwise. So it is minus M V L by 2 cos theta. Okay. Now remain just calculation part. You can see through mass gets cancelled and 1 L gets cancelled. 2 here 6 times and here 2 gets cancelled. V cos theta, sorry, V naught cos theta. This is minus V cos theta. So it is now V naught plus V into cos theta. That is equal to L omega by 6 or into 6 by L. That is now omega. Okay. So here we have taken conservation of angular momentum about point, right? Let us see next one. So your correct option is, it is option D, right? Right. A rod of length L forming an angle theta with horizontal stripes, a frictionless flow at A with its center of mass, velocity V naught, and no angular velocity. Assuming that the impact at A is perfectly elastic, find the angular velocity of the rod immediately after the impact. So the previous question and this question almost the same. Okay. Let us see now how to solve it. So it is given that surface is frictionless. A rod is now. So makes angle theta, velocity just before collision, that is V naught. So we have to find angular velocity, same as previous question. Condition given, it is elastic. Since it is elastic, E value is 1. Okay. Again, writing same equation, assume that after collision, for center of mass, velocity is V. Okay. About this point, right now, conservation of angular momentum. Then see what we are getting here. It is m into V naught L by 2 cos theta. That is equal to I value, I value ml square by 12 omega clockwise. minus minus mv L by 2 cos theta, right? Then see from this what we got omega value. It is 6 into V naught plus V into cos theta upon L, right? This is what we got in the previous problem. Okay. Now see extension for this. So condition given that it is elastic. So observe here which point is making collision. So this end of the rod is making collision with the ground. So focus only for that point and ground, velocity of approach and velocity of separation. Okay. Velocity of approach, it is moving down. Before making collision, rod is having only translatory motion. So for each and every point, velocity equal to V naught. That means for this point also velocity V naught downwards. And that V naught becomes velocity of approach. Okay. Now after collision, after collision, after collision, for center of mass velocity V upwards and rotation is now clockwise. Okay. For center of mass velocity V. So for this point also velocity V upwards. For this point also velocity V upwards because of translation. Because of rotation, velocity for this point, it will be R omega and R value L by 2. It is L by 2. So it is now L by 2 omega. Okay. Now take its velocity component along vertical. Now see carefully, this angle is theta, right? This is a theta, then this is a normal to this one and this is a normal to this, then this also theta. That means for this point, velocity is now V plus L by 2 omega cos theta. That is velocity of this point just after collision. So since it is now elastic collision, velocity of approach equal to velocity of separation. So it is now V plus L by 2 omega cos theta. This is what we got in the last problem. Now extra part is now collision is elastic. So velocity of approach is equal to velocity of separation. Okay. Now in this we have to eliminate V because V is not given. We have to get answer in terms of given quantities, that is V naught and cos theta. Okay. So I am taking from here V value V naught minus L by 2 omega cos theta in this one. So this becomes omega equal to 6 cos theta upon L V naught plus in the place of V. In the place of V, I am writing V naught minus L by 2 omega cos theta. So it is just matter of calculation. Now see what we get. Omega, and here also omega is there. So if I am taking this value inside, L and L gets cancelled. 6 is there. 6 by 2. Okay. Do one thing. Omega equal to 6. V naught, 2 V naught. 6 cos theta by L. This is 2 V naught minus L gets cancelled. 6 by 2, that is 3. 3 omega cos square theta. So I hope calculation is okay. 2 V naught. Okay. Right. 6 by 2, it is 3. Now take this value here. Omega into 1 plus 3 cos square theta. That is equal to 12 V naught cos theta upon L. That means omega value 12 V naught cos theta upon L into 1 plus 3 cos square theta. This is our value. Okay. So previous problem and this problem both almost the same. Okay. Means up to here same only. Extra part is given, it is elastic. Then writing velocity of approach equal to velocity of separation. Remaining solving these two, then getting omega value. Right. Let us see next one. Right. See the question. A cylinder of mass m and radius r is rotated about its axis with angular velocity omega naught as shown and lowered on a rough inclined plane at an angle 30 with the horizontal and mu equal to 1 by root 3. The point of initial contact of cylinder and incline is at a height of 3r from horizontal. Calculate the time taken by it to reach the bottom of incline. Let us see how to start it. Mu value is given 1 by root 3. Angle 30, it is omega naught. We have to calculate initial height is 3r. Time taken by it to reach the bottom of incline. Let's see how to solve it. So first make a diagram for the given data. So diagram is now angle 30. So this is 30. Right, it is now lowered on the inclined plane. Right, you can see rotation is given clockwise. It's a height from horizontal is given as 3r. So we have to find time taken to reach bottom of the incline. Right, mu value 1 by root. Okay. Now see how we are solving it. First of all, calculate. Let's see what is given here. It is only omega is given. Because of rotation, for contact point, velocity will be downwards, right? Because of rotation, velocity for contact point is down the incline. Then friction will be up the incline. Okay. So frictional force will be mu mg cos theta. So I'm writing a frictional force. Frictional force is, that is a mu k into normal reaction. So why mu k means it is now slipping. Okay. This is now mu value 1 by root 3. Normal reaction is mg cos theta. That is root 3 by 2. It is mg by 2. And you can see weight component is now mg sine 30 downwards. It is mg sine 30. So mg sine 30 means mg by 2. mg by 2. This also mg by 2. That means what is net force? Net force is 0. That means acceleration of center of mass is 0. So first conclusion is that mg sin 30 is balanced by frictional force. It is up the incline. So net 0 means acceleration of center of mass is 0. That means it will rotate at same point until omega becomes 0, because due to friction torque will be you can see because of friction torque will be, it is anti-clockwise, but omega is now clockwise. That means until omega becomes 0, it will be at same location. So first focus at what time omega becomes 0. Omega 2 equal to omega 1 plus alpha 2. Omega 2, it is 0. Omega 1, omega naught, that is clockwise. And alpha is now anti-clockwise. It is minus alpha t. So time taken to come to rest, or you can say for omega to become 0, it is omega naught by alpha. So we require now alpha. So to find alpha, we have take torque equation. Torque about center of mass. Torque about center of mass. It is only because of friction. Okay. And frictional force is mg by 2. Frictional force mg by 2 into r. This is now torque, that is equal to I into alpha. Moment of inertia, it is mr square by 2 into alpha. See what is alpha? 2 gets cancelled, mass gets cancelled, 1 r gets cancelled, alpha equal to g by r. Alpha equal to g by r. Right. That means time taken for omega to become 0 is omega naught by alpha. Alpha is now g by r. Okay. And see what happens now. Once omega becomes 0, now question is just like as cylinder is placed on an inclined plane. No velocity, no omega. In such a case, first we have to focus to have rolling without slipping. Minimum coefficient of friction required. In earlier lectures, we have learned that minimum mu value is beta upon 1 plus beta into tan theta. Beta 1 by 2, 1 plus 1 by 2, 3 by 2, tan theta, tan 30, 1 by root 2, 2 gets cancelled. It is now 1 by 3 root 3, right? That is minimum mu value required. But here present 1 by root 3. So this is greater than the required value. That means cylinder rolls down without slipping. In such a case, acceleration of center of mass, it is a g sine theta upon 1 plus beta. Sine 30, 1 by 2, g by 2. This is g by 2. 1 plus beta. It is now 1 plus 1 by 2, that is 3 by 2. So ACM g by 3, right? Now we are given a height equal to 3r. Then this hypotenuse will be 6r, right? Because sine 30 equal to opposite by hypotenuse, right? Then displacement is 6r S equal to half a t square. Let us take it as this is t1. Time taken to for omega to become 0, t1. So take this as t2. So S equal to half a t square. See what we get? 2, 3, 6, 6 and 6, 36. 36. So T2 value 6 root R by G, right? T2 value how much? 6 root R by G because 6, 36. Okay. That means now time taken for the cylinder to reach ground, that is equal to T1 plus T2. T1 R omega naught by G. T2 6 root 6 into root of R by G, right? So that is our final answer. So I hope you got a clarity. First thing we are focusing what is a motion. So we got a clarity that center of mass having no acceleration, only rotation. Okay.